we talked about this linear systems, and you are solving problems with linear systems now. And you, I'm sure that you understood that how various cases can arise from even when I particularly choose a particular pair of people, right? So all of you are, I guess, are convinced of that this system can address several different points, several different ways of dynamics. But two important things are still left, and for that we actually need nonlinear systems like that we had in case of that SIR model that you solved in your previous assessment. There we had a case where you have these three equations, and it was such a system that we could reduce it, but we can also make some systems, we can also have some systems which are not that easily reducible. So the main thing there, in that particular model which was not here present, was interaction. So I was writing down two equations. I was writing down two equations in linear systems where I had these terms like 4x or ax plus 3y or by, something like that. But I was not having any term where I had x multiplied with y, right? No xy term was there. So the main flavor of this model, linear models, were that we were not having any interactions. We are not looking at pictures where something unique happens or something unique phenomena occurs which changes the x and y themselves when x meets y. What happens when x meets y? Okay, this case was important in case of our SIR dynamics, and we had terms like xy there because the number of infected people was changing when a susceptible person meets an infected person. So these are called interaction terms. Okay, and here you see the nonlinearity is coming into the picture because you have x and y coupled together. So if I want to take one step further from linear systems towards nonlinear systems, the first thing I need to understand or learn is that the phase portraits that you are currently drawing, we also drew several phase portraits in our discussion in linear systems, how these phase portraits are supposed to change if I am considering a system where these kind of terms or these kind of x square y, this kind of terms are coming, if they come into the equation, will I have something extra, something more? And how will I understand even how to draw the phase portrait there? So the first step towards learning that, and we will discuss nonlinear systems, nonlinear coupled system for like three, 4 classes after this. But the first tool that I need before we start venturing into that region is to analyze fixed points or analyze fixed points in a more quantitative way, just like that we did in case of linear stability analysis. I guess you remember linear stability analysis. We discussed that for one variable systems. So, and I told you that we can generalize this into 2 variable or more variable systems. If I have a similar kind of trick used, and I can solve that. I can understand the nature of fixed points from there. So this entire thing that we will learn today is a trick, is a tool, a mathematical tool, which is called linearization. So as the name suggests, linearization. Okay. So as the name suggests, it simply means that looking at a system, a particular system which is basically nonlinear in nature. So we'll have some terms like this maybe in a system, but we will try to look into the phase portrait of that system in a linearized, if we from a linearized point of view. So that simply means that if I consider a phase space or phase plane, so to say, where I had trajectories which were like this, nonlinear in nature. Okay, so nonlinear trajectories. If I had trajectories like this, so instead of considering these nonlinear trajectories, I will take a point, a fixed point, and I will focus myself at a very close proximity of this system, just like linear stability analysis. Okay, a very close proximity, and I will try to draw some lines instead of some curves. I'll try to draw some lines around that point, and see if it is a stable or unstable or saddle or what it is. Okay, so like that, if I have several points of the fixed points, saddle points in the dynamics of the system, for each of them, near that point, near very close, in a very close proximity, to try to draw the phase trajectories with a more solid mathematical tool associated with it, and then we will just expand that idea to understand the entire phase trajectory, similar to the linear stability analysis. So here basically I am trying to teach you the trick that if I have a system where x dot is equal to fxy and y dot is equal to gxy, okay, and f and g are not linear functions anymore. I am trying to venture into a system where I have non-linearities present there. So generally speaking, they are all non-linear functions, and I know that x star comma y star is a certain fixed point of dynamics of the system. That simply means that f of x star y star is also 0 and g of x star y star is also 0. So I will equate both this equation to 0 to figure out the solutions x and y from this system. So that is a fixed point. I don't know it's a stable or unstable or what kind of a fixed point it is. And similar to linear stability analysis, I want to understand this in case of two variable systems now. Okay, and then we can generalize the same idea to many variable systems. So the idea will be same. We will start from the same point of perturbation. So we'll consider that two variables u and v, okay, which are x minus x star and y minus y star. Okay, so x is a position. X is a position where the system is currently in the x along x direction. Y is a position along y direction. And I'm seeing that how far they have moved from their fixed points. Okay, so this is kind of a perturbation. You have given a small perturbation to the system which has drifted away a little bit from its previous position, which was a fixed point. So x minus x star and y minus y star are basically small disturbances from the fixed point. Now I have to see the same way we did in linear stability. We will have to see that if I cause such a small disturbance, will this increase with time or will this decrease with time? So I want to figure out that what happens to u with time, u dot. Okay, what happens to u with time, what happens to v with time, what kind of solutions they are. And we have shown that if they exponentially increase, that means the perturbation is growing, and if you cause a little bit of perturbation, they will move away from it, and we are talking about something unstable there. And if they exponentially decrease and fall upon the fixed point once again, then it is a stable fixed point or something like that. So a similar idea can hold here as well. Similar idea can hold here as well for two variable systems, and we'll try to see what it is. So let us do a small mathematical analysis similar to that and see what u dot is. So if u is defined as x minus x star, and x star is a number, right? X star, y star is basically solutions of these two equations. So x star is just a number. So u dot will be x dot, right? V dot will be y dot, right? I'm not calculating for v right now, only x. For u, let us do the analysis, and from there we can identify that what will happen to v. So u dot is equal to x dot, right? Now same thing, substitution and then expansion, Taylor series expansion. So u dot is equal to x dot, but x dot is equal to fx. Okay, so f of fx is basically x star plus u, y star plus v, right? fxy, x is given by u plus x star, v plus y star is y. Okay, so let us proceed then. Now I have a two variable system, expansion for two variable functions. How to do that? Tell me what will be the Taylor series expansion of this if I want to expand this from the around the fixed point x star y star. What should be the expansion? So expanding a two variable function, two variable Taylor series expansion. Okay, so f of x star plus u y star plus v, expanding it, f of x star y star. Just do the same thing for two variable systems, right? So u del f by del x, okay, v del y plus the higher order terms, order of u square, v square, and so on. So just take u and v as your delta x, delta y. Okay. So I'm expanding from around x star y star. So these are like 0, 0, x star y star is my stable point, and these are my delta x, delta y. So this is how we expand, right? Taylor series. What is the value of the first term? 0, right? Because that is how we figured out x star and y star, by equating f xy equal to 0 and g xy equal to 0, right? So f of x star y star must be equal to 0. So that simply means that f of x star y star is equal to 0. The first term is 0. So what are we left with? We are left with u del f del x plus v del f del y and some higher order terms of u square, v square, and uv, right? So these terms are there, and more higher order terms. This is 0 because this is a fixed point. So same analysis we did in case of linear stability. Okay, fine. Now if we are okay up to this point, can you tell me that what is going to be, this is u dot, right? We started with u dot. What is going to be v dot then? A similar analysis I can do, writing it in as y dot, then g in terms of g, same thing I can write, because the equation for v was gxy, right? So what will be v dot? So what will be the expression for v dot? Just by symmetry you can see, right? If the first term that is lying with u is del f del x, then what should be the first term lying with u here? Del g del x. And the second term with v must be del g del y, because g and f are both functions of x and y. And here also I will have these higher order terms of u square, v square, and v. Okay. So now just see that if I now ignore this, all these quadratic terms, if I ignore these higher order terms altogether, then I am left with an equation, a set of equation which looks like this: u dot, v dot. So two variables, u and v, and I am looking at their time evolution. And here I have u, v. Okay. And here are the four coefficients. What are these four coefficients? Del f del x at x star y star, del f del y at x star y star, del g del x at x star y star, and del g del y at x star y star. So I am writing x star y star below here. Okay. So these are all numbers, right? Del f del, calculate the functions differential and put the value x star y star, you get a number. Here also, all the four terms, you get some numbers out of it. Okay. And what is it? This is basically a linear system, right? This is basically a linear system while you are looking at two time evolutions, time evolutions of u and v in terms of linear dependencies. There is no term like u square, v square, uv, or some higher order interactions. Okay. So this, what we have done here, is basically called the linearized version of the system that we started to deal with, where we had these general functions f and g, which were nonlinear in nature. But what are we doing here? We are writing down a Jacobian matrix for that particular system. This is the Jacobian matrix, right? You know the definition of how a Jacobian looks like. The Jacobian matrix at the fixed point x star y star. And by putting it, this becomes this entire thing, this entire matrix, if we call it A, this matrix basically becomes an analog of that f prime x star that we had in case of simple one variable systems, where we decided that depending on their positive or negative sign, we decided that this is going to be a fixed point which is stable or unstable, right? So for linear, if you remember, for one variable systems, we just did this entire thing based on one calculation of f prime x star. We took f, we took derivative of that, and then we put the value of fixed point and checked if it is positive or negative, and this was enough to tell me that this is going to be fixed point stable or unstable. Now in two variable systems, this entire matrix, okay, this is basically an equivalent or analog of this thing in two variable systems. Okay, so this matrix serves the purpose, and from here you linearize the system, and from here you can decide that if you just ignore the other non-linearities of the system and look at the linear part of the trajectories, we are just looking at small perturbation. This means you are ignoring u square, v square, means you are just looking at small perturbations of the system, and you are looking at the phase portrait in a very confined small periphery, small neighborhood around the fixed point. It will tell you that it is a stable point or unstable point, or what kind of a point it is. Okay, so this is the trick of linear stability analysis or linearization of a system in two variable systems. You can also generalize it to three variable or higher variable systems. Only linear terms you have to keep, non-linear terms you have to throw away, and this will give you this matrix A that will conclude for you that stability of the system. So here, instead of finding f prime x star, you diagonalize this and figure out the eigenvalues and eigenvectors of this matrix, and that is going to tell you that which direction is the strongest direction, which eigenvalue is the strongest eigenvalue, and so on. So the most interesting thing here, by mentioning which I will conclude today, is that the robust cases, which we can just categorize the entire fixed point diagram, entire Poincare diagram that we had, into two segments, where we call all the sources, sinks, like the nodes where the source or sinks and saddles, as very robust cases. Why? Because if you do this linear stability analysis, or you deal with only the linearized system, and you have some nonlinear terms present in the system, still the analysis with only the linearized part of it gives you very accurate result about how the system behaves. Okay, so that means that you can draw the entire phase space. If you have source and sinks, you can accurately draw that by only considering a linear equivalent of the system, linearized system, where you ignore the higher order terms. Okay, but the centers, the rotations that we have seen, the centers where both the eigenvalues were purely imaginary, that is a very critical marginal case, which is very easily affected by addition of some nonlinear terms. Okay, so in that perspective, we more coarsely classify the fixed points into two categories. The first one are the robust cases, which include the repellers, that is the sources where both eigenvalues are positive and the real part is positive. Okay, so this includes both the spirals as well as the nodes. Okay, repellers and attractors, we are calling them in general repellers and attractors, where the eigenvalues have negative real part or the eigenvalues have positive real part. So only based on the real part of the eigenvalues you can categorize them as repellers and attractors and saddles. So these are all robust cases which basically could be understood simply on the ground of this simple mathematical formula. Okay, and only for centers you need to take a step forward and look at the nonlinear terms, which sometimes gives you wrong result if there are centers present. Okay, otherwise this is completely fine. So all these fixed points where you have eigenvalues of this matrix, let me just write it very clearly. The eigenvalues of this matrix, if the real part of lambda of this matrix, okay, real part of lambda of this matrix is non-zero, either positive or negative, okay, or one positive, one negative. If you two variables, so one positive, one negative is also a possibility. Then you have either repellers or attractors or saddles. These can be analyzed simply by the linearized form of it, okay. And all these particular cases where you have real part of lambda not equal to 0, there is also a name for it. We call it hyperbolic fixed points. So all these fixed points, they could be, remember, fixed point does not mean that just you have a node. It includes all the spirals and everything. So wherever you have eigenvalues, real or imaginary part, real part present, not 0, they are called hyperbolic fixed points, and they can be analyzed simply by this matrix. You can draw the entire phase portrait, the global phase portrait, faithfully relying on the local phase portrait. Okay, so the local phase portrait basically reflects what the global phase portrait is going to be. So I will stop here today, and in the next class I want to discuss a full example based defining a model. We will discuss a full example where all these different cases will arise, and you will see that you don't have to guess, or you don't have to do some tough mathematics. You can simply linearize the system and understand a simple nonlinear system. So we'll start dealing with our first two variable nonlinear coupled system. Okay, so I will stop here for today.